Hello, guys. I hope you're having a great spring break. We did go over this problem in class, but I'd like to go over this one more time. It's a good review. So the problem says a uniform beam of length 4 meters and mass 12 kilograms is supported at the center by a pivot point. A 20-kilogram mass is hung 1 meter from the left of the beam. Where should the 30-kilogram mass be hung from the right to keep the beam in rotational equilibrium? So we don't know where we should hang this 30-kilogram mass, but we already know that we can use torque. So the sum of the torques is equal to the force times sine of theta. In this case, since we are applying a force directly at a 90-degree angle, we know that sine of theta should be sine of 90 degrees, which is 1. Therefore, we can just use F sine theta. And we know the force experiencing that this 20-kilogram mass is experiencing is directly downwards. The force is the mass times the acceleration. In this case, we are looking at a 20-kilogram mass, and it's being accelerated downward at 9.8 meters per second squared. That's the acceleration due to gravity. So this is the weight. So that means my torque on the left hand side is 20 times 9.8, which gives us, if we do that on the calculator, 196 Newton meters. 196 Newton meters. Now, that is a clockwise torque to the left, so we know that is positive. Counterclockwise torque will be to the right hand side. We know that the mass is 30 kilograms, and we do not know the distance, so I'm just gonna call that x, and that should be equal to the 196 Newton meters. So if we set torque the left hand side equal to the torque on the right hand side, all we have to do is multiply the mass times the acceleration again, going back to this 9.8. I'm just going to get rid of the units for now. So we have 9.8 times 30. That's the force or the weight on the right hand side, times the distance, which we do not know. Set that equal to the torque on the left hand side. And now all we have to do is solve for x. 9.8 times 30 gives us 294. 294 x, and that is equal to 196. Since we want this to be in equilibrium, we have to set them equal to each other. Divide both sides by 294, and we are left with x equals about 0.666 meters. So the 30-kilogram mass should be placed about 0.66 meters from the right end. Part B says, what is the net torque acting on the system if the 30-kilogram mass is placed 0.5 meters too far to the right? So we know that the mass to be in equilibrium should be at 0.666 meters from the right. So that means that if we're placing it 0.5 meters too far to the right, that should be 0.666 plus 0.5, which gives us about 1.166 meters. That's our new location. The new torque would be 30, right? That's the mass on the right hand side times gravity, 9.8. So this whole thing is the force or the weight times, remember it's force times the distance. Sorry, I forgot R. The distance is now 1.166. So when you multiply all that out, you're left with the new torque equaling to 343.5 Newton meters. So if we account for the torque on the left hand side, that should be 343.5 minus 196, which gives us a total torque counterclockwise of 147.5 Newton meters.